What? He told you I can't just rely on my own. So what am I going to do? I will bring two others. I will place one here so it passes through a current, and the other on the other side so it passes through a current. And thus, in this case, I now have the operating coil, and on the other side I have the magnet with the local coil and the remote coil attached to it. So how will this work for me? Let's see together. Let's say now that you have two different things. Either you have an external voltage or you have an internal voltage. If we start with the external voltage topic, the external voltage will move in the direction of the voltage. For me, as a protection zone, I see where the currents equal the currents. As a primary, I am speaking as a primary, I see that the situation is very stable and there are no problems for you. The secondary current here will move relative to the local in the opposite direction, and also relative to the remote, and both will continue to circulate around each other. Of course, here, due to the presence of ratio error and other factors we mentioned, there will be a difference between your two sides. Consequently, in this case, the current that will flow in the relay is the sum of the commercial currents or the difference between the two. As for the local and remote, as you can see, the local current will move in this direction and the remote current will move in that direction. In other words, here we find that the directions of the local and remote currents are essentially in the same direction. So this leads us to the fact that the torque generated from the local and the torque generated from the remote both support each other, resulting in a very large torque. While on the other side, the current flowing is the differential current, and thus it will generate torque only as a result of the difference between the currents. But here, the sum of the currents, remember what we all learned, for example, in university when they tell you that here the torque generally is proportional to what? To N times I, which is the number of turns, Q times the current. So here you have N, which is the number of turns multiplied by the difference between the currents. However, here you have N times the sum of the currents, and thus the opposing torque is greater than this torque. Now, this torque is called the operating torque. Why? Because its presence is what turns the disk to operate the protection relay. As for the other, we call it the biasing, because it is biased or inclined towards something, or it restrains or breaks this thing, or it is what leads to stability in the situation. That's why we can say that we refer to it in the case where it is greater than your, and in the case where the L is greater than the EA, your torque. And thus, I have reached the stability type stage. As for when I have, as you can see here in my setup, in this case, how will the directions of the currents flow? Well, both of them will have reversed and entered into my setup, and consequently the currents will be like this. Here we will notice that there will be a group of currents moving in my direction, and if not, it will equal a group of currents moving algebraically as well, because the currents have completely reversed. Meanwhile, the local and remote coils, which are specific to the local current here, are moving opposite to the remote current. Consequently, their currents will be like this. In this case, I will have a situation where it aligns with being multiplied by it. The difference between these currents will be that there is a group of currents, and therefore you will have this result here, because you have greater than or equal to, and thus I was able to overcome the problems or obstacles that were facing me in it. The Metz price configuration. We will stop here for this lecture, and hopefully in the next lecture we will start to look at the transformer differential protections